Hi, this is Dan Steinberg at Salford Systems, and welcome to this particular edition of Salford Systems online training videos. Today's session is devoted to TreeNet. We're going to explain what TreeNet is, why you should be paying attention to it, and why you need to learn more about this amazing technology. This is a short presentation only. There will be longer ones which will allow you to dig into the details. TreeNet can be summarized in perhaps three words: speed, power, and accuracy. TreeNet is Salford Systems' most powerful data mining technology. What's special about it? First, it's fast. It will allow you to work through large databases and handle many predictors in record time. That speed wouldn't be worth very much if you didn't get accuracy. There is phenomenal performance that can be obtained from TreeNet models. These models can be far more accurate than you thought could be possible with modern machine learning methods. Further, it's automatic. A great deal of what TreeNet does, it does with no user intervention or very little guidance from the modeler. It doesn't mean that the modeler can't help, and the modeler has an important role. But even doing nothing in order to guide TreeNet is very often able to get you to very good results. TreeNet handles problematic data effortlessly. You can have data that has errors in it. You can have data that makes mistakes regarding the actual dependent variable. You can have outliers. You can have missing values. All of those things are challenges for any data mining technology. They're less of a challenge when it comes to TreeNet. TreeNet performs extremely well in classification problems, problems in which you have a yes-no, good-bad outcome. It's also extremely good for regression when you're trying to predict something like how many days will a person end up staying in a hospital? How much will a person spend when they visit a website? And TreeNet has been shown to be extremely good in the analysis of textual data, but that's the subject of another video and a set of tutorials related to text mining, but TreeNet is very relevant to that topic also. Why are we excited about TreeNet? Well, first of all, it's been responsible for numerous wins in data mining competitions going all the way back to 2002. In other words, we have a decade's worth of track record in terms of excellent performance of TreeNet. This technology is indisputably state of the art. So what exactly is TreeNet? Well, TreeNet was invented in 1999 by Stanford University data mining visionary Jerome H. Friedman. As many of you know, we've been working together closely with Jerry Friedman ever since 1990. Friedman is the principal author, in fact, the only author of the actual CART software. He's a co-author of the book on CART, and he's the only author of Mars and other groundbreaking predictive modeling technologies. All of the tools which Salford Systems offers are built on Friedman's proprietary source code, which is available only through Salford Systems. You may find that there are other vendors that claim to offer something similar, but the only real versions are available from Salford Systems. TreeNet version 1 was released by Salford in 2000 and is installed in many large-scale mission-critical business intelligence systems. TreeNet was described originally as stochastic gradient boosting. That's a technical description. There is an awful lot written about that topic right now. This topic was invented by Jerry Friedman, and we are the first to have brought this technology to market. It's easily the most powerful off-the-shelf technology in existence. The TreeNet technology can be simply described at a high level, although the details are very complex and hidden from view. For the user, you don't need to start understanding those technical details, and you can gradually gain mastery of them. TreeNet is a learning machine that uncovers structure and data through many stages of discovery. Each stage is intended to learn only a little, and hundreds or thousands, sometimes even tens of thousands of stages may be needed to arrive at a final model. However, all this can happen very quickly, as we'll see when we run the software. TreeNet typically builds very small cart trees and combines many such small trees into a powerful model, far more powerful than you can obtain from any single tree model. The TreeNet strategy is to start simple. What do? We grow a simple cart tree with only a few nodes. The default in TreeNet and the recommended number to start with is 6. You can always change that to another number, either smaller or larger, and you can vary the size quite a bit, but extensive experience has suggested that 6 terminal nodes is a very good default, a very good place to start, and most likely it will turn out to be the best for your problem as well. This tree can either be a classification tree or a regression tree. Now, in most circumstances, a 6-terminal node tree is going to be too simple to be very accurate. Hence, it makes mistakes. And what is the nature of a mistake in a decision tree? Well, let's suppose this is a yes-no outcome, and the example we're going to run very shortly has good and bad outcomes, and suppose that we're trying to predict the bads. Well, in that case, we could color code the terminal nodes so that the red terminal nodes are intended to flag the bads. Well, in a model that's too simple, these terminal nodes are not going to be pure. What we mean by this is that, sure, this red node here may be very nice in that it has concentrated relatively more bads than goods compared to the overall population, but this node may still contain a reasonable number of goods. And similarly, blue, which is indicating here good, may not be pure. The node may also contain some bads. So what that means is that a simple model like this, even though it may perform moderately well, is going to be making mistakes in the outcomes, the point at which the tree makes this predictions. So what can we do about that? We can focus on the mistakes that the simple tree makes. Those mistakes could be mistakes in classification, assignment of a probability, or a regression prediction. So we're going to measure the mistakes by some form of residual, and we don't want to get into the details here of how we do that. It's clear in the case of regression that a residual is a difference between the real outcome and what the model predicts. And what we're going to do is we're going to take those errors or residuals and we're going to make them a new dependent variable, and we're going to build a completely new model to predict the errors. And notice we now have a different tree with a different pattern and a different shape, and this is the pattern of the tree that is intended to correct the mistakes of the first tree. Here's what's interesting about this. The second tree is grown using all of the training data. If we were to have tried to elaborate our original tree using a conventional tree methodology, the tree would have just become bigger, which means that the data inside of the nodes would have become diminished as the tree grew. But because we are growing a second tree on the errors of the first tree, we actually get to start with all the data again. And this is one of the key secrets to the success of this technology. Every stage of learning starts again with all of the data, and we don't suffer the principal challenge of decision trees in which we are working with progressively less and less data as we work our way down the tree. So what do we have now? We have a revised model with 2 trees. This was the first one, and this was the second one. And the way in which we combine them is simply to treat each tree as if it is generating a score. And so here's a tree that generates some scores. Here's a second tree that generates different scores. And we take the score for any record that comes from the first tree, and we add to it the score that comes from the second tree. The second tree can therefore be thought of as correcting or modifying the prediction of the first tree. So a model at the end of a TreeNet process is simply the sum of all the scores of all the trees that were built. Here's an example of now a third stage in which we go and continue that same process, and there is no limit to the number of stages that we can take this process through. What I've done here is I opened the Sulfur Predictive Modeler. You should be doing the same if you want to follow along with me in these slides, or if you want to follow along when you listen to these training videos a second time. In addition, I've opened a file called goodbadx_10kc.csv. That's a file which is available to you from our website. Please visit the website and go to the areas that you've been pointed to find the training data files, and make sure you have this one available. It has 9,874 records. It's only got 20 variables on it. 5 are character, 15 are numeric, and this data pertains to a good-bad outcome, which is why we gave the data set that name. Let's go ahead and go directly to modeling, even though that isn't what we would normally do if we were trying to get an appreciation of a data set for the very first time. Let's click on the modeling button here and observe what I'm going to do. The first thing I'm going to do, as always, is indicate which is my dependent variable, and I know that already. That is going to be the good-bad outcome, which is coded as a text variable as the word good or the word bad. Here we have 19 available predictors. It turns out we don't want to use all of them because there is a variable called ID, which is there simply to allow us to track records as we manipulate them in future models and perhaps make predictions. So let's simply remove that from the list. We don't want an ID variable in there. Other than that, the remaining variables are in fact perfectly legitimate predictors. There's only one other little detail I want to take care of here, and that is that the variable occupation is coded 1, 2, 3, etc. However, it represents occupations. It just so happens that this data was transformed from the original description into a numeric one in order to help disguise the identity of the data. Other than that, there was no reason to have done this. We'll just go ahead and click that that's categorical, and we are actually ready to go. I will want to do a couple of other things here. Because we're talking about TreeNet, let's choose TreeNet as the data mining engine that we want to work with. And I am going to set the number of trees that we're going to grow to 500. The default is 200. We generally think that that is not a bad place to start, but it is almost never the place you're going to end. So we want to allow some more trees here. The only other change that I'm going to make is that when it comes to testing, instead of using cross-validation, with almost 10,000 records, we can well afford to reserve a good chunk of the data for testing. I'm going to reserve 50%. Other than that, nothing more that we have to worry about. Going back to the model statement, the model tab, just wanted to make sure that we're focused on the right kind of model. This is a yes-no outcome or a two-class outcome for which the recommended option is logistic binary. So let's go ahead and click the Start button and see what happens. So you can see that the process of going through 500 trees on this data set of 10,000 records is in fact fairly rapid. So what I told you before, about TreeNet speed is, I hope, now evident to you. I will also point out that I happen to be running this particular example on a Windows XP virtual machine, which is being hosted on a MacBook Pro. In other words, it's very likely that in your own offices you would be working with a machine that's even more powerful than this one. So we have come back with a very high-level description of what's happened here. And we have some curves here that are representing the performance of the model as we go through the training data, which is the blue line, and as we go through the test data, which is the red line. We would like these two curves to be very close. That's an indication that we're not overfitting. These curves here are a little bit further apart than I would like, but not so far apart as to be seriously concerned. The particular curve that we're showing here is related to log likelihood. This is something that not everybody prefers to look at. So we can also have a look at, for example, area under the ROC curve. And this model is performing extremely well. So if I make this bigger over here, we can see that even from the very first trees, we get a very high performance. And then this gets driven up to an extremely high level. Not necessarily something that you should expect for all such models, but it did happen this time around. Let's get it back to a size I'm more familiar with. And now let's look at some of the results. So we can go to the summary display first. Look over here at prediction success, which is the confusion matrix, the classification matrix. Let's look at test data. What we see here is that the bads on test data are predicted correctly 93% of the time, and the goods on test data are predicted more than 95% of the time. So this is actually very high performance. If we think of being mostly concerned about getting the bads right, well, we had 2,841 bads, and this model makes mistakes on only 198 of them. Okay, so what else do we see from the summary table? Variable importance. The variable importance list is telling us which variables are driving the performance of the model. And what we see at the top is excess to Blue Book, which is a measure of how much of a gap there is between what the borrower is intending to pay for the car and what the Blue Book value of the car is. Now, if it's a new car, then there will be some other measure for this, but if it's a used car, then of course there is an established market and some typical value for that particular make, model, adjusting for the conditions of that particular model. Next, we have the age of the vehicle. Following that, we have bureau searches in the most recent month. This is evidence in the credit bureau records that this borrower was seeking to obtain credit somewhere else. Then we have the occupation, some information related to some previous bad outcomes, if any, for the borrower, the residential status, more about searches in the last 6 months, disposable income, time at the present employer, and we actually have made use of every variable in this particular list of predictors, but the relative importance drops very quickly as we move past the top 4 predictors. So we may want to take that variable importance ranking here quite seriously to think about a simpler model. But that's not that interesting. Here's the part that's more fun when it comes to this model. Let's try to get a good understanding of what goes on here. So I clicked on the create plots. Now I just want to see one-way plots right here. That is, I don't want to look at interactions. And I'm going to select all here. We don't have that many graphs, so there's no reason to really try to save time here in generating them, and let's do create plots. Here are all the plots that have been created. It's for the 320 tree optimal model, and I can click on any one of these in order to see the graph, or I'll just click on show all here and we'll see the entire bunch. Scrolling down here, we see small pictures displaying each variable. Let's double click on one of these to get a better view. So what we see here, in the age of the vehicle, which is measured in days, we can see here that at about 1 year, the vehicle, anyone who's wanting to buy a 1-year-old car is actually less likely to be good than someone that's buying a much newer car. This particular description over here says we're predicting for the good-bad status being good, and therefore moving upwards on the y-axis is increasing the probability of being good. So older vehicles are associated with being less good, but there's a flattening out of this curve over here. So really we're looking at relatively new cars here, and then cars 1 year and older in this segment of the graph over here. Let's look at a categorical variable which has some good descriptions of the levels. And what we see over here, residential status. Quite interesting. If someone is an owner of their home, then this pushes in the direction of them being good when it comes to being a borrower. If they're buying, this is also good when it comes to borrowing. Rooming with other people is the worst status that we see in this data set. Living with parents, slightly negative. Mobile home is fairly close to living with parents. And then, of course, we don't really know what other stands for in this particular population, but it's a grab bag and also is in the negative direction. Scanning here through a few more of the graphs. Here's another one where the results won't be surprising, but still let's have a look at it. What we see over here is for this particular population of borrowers, the status of being married is best. Single means never married. That's second best. Separated is probably worst when it comes to the probability of successfully repaying this loan. Divorced, which is possibly a status that might come after separated, is a little bit better. And then people living together but not married are also in a status which is worse than either married or single when it comes to predictability for repaying this loan. Now let's look at deposit to cash price. The larger the fraction of the total cost of the vehicle that is paid as a down payment, the more likely the loan is to stay good. Not a surprise. The curve is a little bit wiggly. We'll say more about that in other videos about TreeNet, but the overall picture is kind of interesting. And what we see here is that there's a flattening out towards the right end of this particular curve, which is very important to know in case you are using this investigation of the data in order to try to understand the potential non-linearity between any predictor in the outcome. Another no surprise indicator, if someone has a mortgage, then of course they are in a better status than if they don't, but that is similar to that other variable that we saw before, which is residential status. Here's something which others have observed in similar types of studies, but nevertheless interesting. When a person applies for an automobile loan, they also have to indicate how long they want that loan to have as a term, meaning how many months they're requesting in order to be able to pay off the loan. And it's not surprising that someone who needs 5 years to pay off the car loan is going to be a greater risk than someone that needs less. For example, in this case, the sweet spot seems to be 3.5 years. What is not so obvious, and we don't really have a good explanation as to why the 24-month approximately time period should be slightly worse than the somewhat longer time period. Okay, so one of the things that you can see from this is that we get a very nice intuition and either confirmation or disconfirmation of patterns that we expect to see in the data. And we also get to see the specific relationship in fairly detailed form as to how a particular predictor affects the outcome Y. There's much more that we can say about TreeNet at this point. We simply want to go back to our slides in order to make a final observation. And that is this. TreeNet can quickly deliver world-class models. What we mean by that is that the performance in terms of prediction on new data will be world-class. The methodology itself is a state-of-the-art machine learning methodology. At this point in time, many independent researchers in the field will agree with us that this is, in terms of off-the-shelf, meaning general, not custom-built software for a particular problem, that this is the state-of-the-art. TreeNet will make a good modeler better and will help a less experienced modeler reach impressive results and quickly. What can we do with the TreeNet model in terms of trying to explain it to non-technical individuals and managers? Well, we can display interpretive diagrams in order to explain the model details. We can use variable importance rankings to reveal the key model drivers. The model itself can be genuinely complex, comprising hundreds or thousands of trees, but this is something for the scoring server to manage. It's a IT problem and not necessarily a modeler's problem. Now, there's more to say about how to work with IT in terms of making sure that the models that you develop do not cause a problem for that part of your organization. And that also is something that we'll talk about in another session. Again, thank you very much for joining us, and we hope to be having you as a visitor again to the Salford video trainings. Thank you.